Well, very good morning to all of you. Thank you for joining us. This is Darrell Bruggink, Executive Editor for No-Till Farmer, and I want to welcome you to part 2 in our Gypsum webinar series sponsored by GYPSOIL brand Gypsum. And today our presenters are Ron Chamberlain, who's the lead agronomist and director of the GYPSOIL division, also Patrick McGinnity, the National Sales Manager for GYPSOIL, and we also have a special guest today, Allen Torbert, who is the soil scientist and research leader with USDA's Ag Research Service's National Soil Dynamics Laboratory down in Auburn, Alabama. So welcome to Allen. We had a real successful start to the first webinar in this 3-part series 2 weeks ago, and we're really looking forward to getting into more specifics as to how gypsum can improve the no-till soil profile. Before we turn the controls over to Pat McGinnity, I have a couple of housekeeping items for you. On your screen, there is an arrow you can click on that will open up a question field and it'll allow you to submit questions at any time during the presentation. So with time permitting here at the end of the webinar, we will look to answer as many questions as possible. And then for those that joined us a few minutes before the webinar started, of course you saw a couple of poll questions. Thank you for answering those, and we'll have probably a couple more that are going to pop up while we transition to the different speakers. So we'd appreciate if you just participate in those polls. Do know that those will drop off your screen fairly quickly if you don't answer them, and then you'll be able to see the presentation again. So we'll look to share those results with you after the webinar. So with that said, I think we're about ready to start here. And thank you again for joining us. And I'm going to turn over the controls to Pat McGinnity. And with that, Pat, take it away.
So we'd like to talk today about gypsum and how it can be a valuable tool that will contribute to you guys improving soil quality. I thought what I'd do is first just quickly review some of the highlights from our first talk. We're going to talk about what is gypsum, and then Ron's going to come on and talk about no-till problems that gypsum can solve. And then Dr. Norbert will fill you in on some USDA research that has looked at the use of gypsum in a lot of very important areas, and we'll follow that up with a Q&A session at the very end. We want to talk about what is gypsum. Gypsum, well, it's an older technology. The product itself is calcium sulfate dihydrate, and that is a calcium sulfate molecule that's complexed with 2 molecules of water. And this is the highly available form of gypsum. It releases the calcium and the sulfate for use by the plant and goes to work in the soil right away as a soil amendment. A typical analysis is about 20% calcium or 16% sulfur. A ton of that then translates into contributing 400 pounds of calcium and 320 pounds of sulfate sulfur. As I mentioned, gypsum is kind of an older technology. Ben Franklin used to write about the use of gypsum on his own farms. But to date, it's been mostly comes from mines, and these mines are located in the central Midwest and central Iowa, parts of Michigan, and scattered around various parts of the country. And when you're close to the mines, it's economical to use this type of product, but the further away you get, the transportation costs have made this type of gypsum, the mine gypsum, rather expensive to use, so it's limited its availability mostly to specialty crops. But that is changing with the development of other sources of gypsum. This other source, if you look at the Clean Air Amendment from the early 90s, the Clean Air Amendment really restricted the release of sulfur into the air from coal-fired power plants, as well as it reduced the amount of sulfur in diesel fuel. So where we used to get our sulfur for free in the form of acid rain, that part has been diminished greatly, and we're starting to see sulfur shortages in our soil. And these power plants, as they have looked at removing that sulfur from their emissions, they're using a 2-step process to remove it, and the byproduct that's produced is a very clean and pure form of gypsum, what we call FGD gypsum, or flue gas desulfurized gypsum. There's also other manufacturing processes that are producing gypsum, such as food-grade citric acid plants or a food-grade lactic acid plant. Their byproduct is also gypsum. So we're making other forms of gypsum much more available. As I mentioned, the production of FGD gypsum is really a 2-part process. It starts with calcium carbonate or purified limestone, which is used to trap the sulfite that's had been emitted through the smokestacks of power plants. This process is really preceded by the removal of particulate matter, heavy metals, and nitrous oxide compounds to clean up the emissions prior to their trapping with the limestone. The two-part process starts with taking limestone or calcium carbonate, reacting it with the sulfite gas, and producing calcium sulfite and CO2. That calcium sulfite then is reacted with water and oxygen, and the oxidized form, the byproduct that's produced, is calcium sulfate dihydrate, or what I described as gypsum in the first slide. This FGD gypsum is expected to expand dramatically in supply, mainly because as power plants are improving their scrubbing technology, they had been landfilling a lot of this waste byproduct, only to find out that it's a valuable tool for agricultural production. So they're releasing the supplies more to be applied to soil and removing it from the landfills. FGD gypsum is a carefully regulated product, and it's regulated on a state-by-state basis and really a two-step process. Because it's an industrial byproduct or an industrial waste, usually it's a state Department of Agriculture, a state pollution control agency, or Department of Natural Resources that regulates the use or the release of this for agricultural applications. Once that permit has been developed, then the Department of Ag comes in and registers it as a soil amendment or a fertilizer, depending upon its use. And we at GYPSOIL, we're developing these partnerships with the power plants. So we're a primary liaison with these types of suppliers to get gypsum in a very pure form available to the agricultural distributors, ag retailers, and ultimately the end-use farmer. The typical characteristics of FGD gypsum is it's a fine, damp powder. It's really damp to the touch, tan in color, usually comes out at about 8 to 10% moisture. It can be spread with most types of lime spreaders or broadcast manure type spreaders. Gypsum from a manufacturing plant is usually a white to gray powder and about 8 to 10% moisture as well. Very pure and clean product. One of the misconceptions about gypsum is that it affects soil pH. Gypsum is not a liming agent, so it does not affect pH the way lime does. The fine particle gypsum is a highly water soluble available form of calcium and sulfur for the plant, as well as a soil amendment for the soil. And because of this solubility, it moves into the soil very readily with rainfall, making it a real valuable tool for a no-till farmer. New FGD gypsum is a safe and effective product. It's very low in trace elements and other types of contaminants. The EPA and the USDA have done a joint study looking at heavy metals and contaminants in FGD gypsum, and they've done a very rigorous assessment of it. The report has not been issued, but will soon be released. But Dr. Rufus Cheney, who has coordinated this study, has suggested that they're finding no impact of heavy metal contaminants or other types of contaminants that would restrict the use of FGD gypsum on agricultural soils, making it a pretty safe product to use. With that, I'm going to pass this back to Ron. Let Ron talk to you about problems that gypsum can solve for a no-till farmer. Ron?
Okay, very good. Again, thank you, Patrick. I am Ron Chamberlain, Director and Agronomist for GYPSOIL Division of Beneficiary Reuse Management. It's a pleasure to speak with you this morning. If you would take just a few moments here and answer the questions on your screen, I would appreciate it. As we move forward this morning, I've had several years of experience with gypsum on particularly no-till soils, and one of the things that has been very interesting to me has been the improvement in the soils over time consistently across no-till, and I'm excited to talk with you all this morning about this. Let's talk now about some of the problems that gypsum can solve. Common problems in no-till and other tillage systems, very common: slow water infiltration, ponding and runoffs and leaching, poor water holding capacity, surface sealing or crushing, erosion of soil, nutrients, pesticides, etc., poor rooting, nutrient deficiencies, and just general lower crop productivity versus potential. And this is really related directly to soil structure, poor soil structure, and the soil on the left, which is dealing with compaction and poor structure, generally this is driven by an imbalance of the chemistry of the soil together with the tillage practices, the environment, and so on. And so what we have here is what we call a dispersed soil. It does not have good structure. It doesn't have much oxygen in that soil. It does not absorb water very readily, a poor rooting environment, and just not as productive as it could be. That same soil, though, on the other side where the chemistry has been balanced, the soil becomes flocculated and aggregates, and we've got adequate oxygen in that soil, plenty of space for roots and soil biology to work, and here we have just a much better productive soil. So we look at the components of soil. Typically, soil is made up of mineral, air, water, and organic matter, and these are the balances in which a really productive soil is. And as you can see, it needs 25% of that soil volume to be oxygen. And in many cases, we don't have that much oxygen in the soil just because of the compaction that's the result in a poor soil structure. So let's take a look now at the components, the properties of the soil. When the soil chemistry is out of balance, as it is in this particular case where we have compactable soil, that affects the physical structure of the soil, and as a result, without having the adequate oxygen that we need in the soil, the biological systems are not working either. So when one of those components is out of balance, it affects all three. And our goal here is to move the soil into that center area where all three are in balance, where we've got soil health. So that sweet spot is really our goal. If we look at the types of soils that are appropriate for gypsum, there's only a very small amount of soil that really will not respond to gypsum, and that's pretty much pure sand and pure silt. The rest of the soils in the soil triangle, if they have these issues, can respond to gypsum. So let's talk about soil structure. Soil clay particles and organic matter have negative charges on their surfaces, and those charges attract positive charged nutrients, calcium, potassium, hydrogen, ammonium, and many others. And it's that combination of those, particularly around the calcium, that has a double positive charge that's attaching those clay particles to it, that gives the soil its structure. So let's see what's happening then in terms of pore structure. The chemistry being out of balance, where in this case we have too much magnesium. The magnesium does not have the ability to attract those clay particles tightly. They're very loosely bound. And so if a rain droplet would hit that soil particle, the clay is going to be dislodged from that, and we lose our structure. If we drive over it with a piece of machinery, it is compacted flat and drives the air out, and that soil is not able to do what it needs to. On the other hand, if we look at the soil on the right-hand side, where we have adequate calcium in the soil, the calcium has the ability to bond those clay particles very, very tightly to itself, giving that soil much structural stability, and then that soil has the ability to aggregate and to gather air spaces and be a much more productive soil. So we really want to move from the dispersed soil into more of a flocculated, aggregated type soil. How do we do that? Well, that's where gypsum comes in. Gypsum calcium sulfate, as Patrick mentioned earlier, we apply that to the field. It rains on the gypsum on the field. The calcium dissociates from the sulfate, and then the sulfate binds up with the excess magnesium that's in the soil, creating a new compound, Epsom salts, which is soluble, so it moves down deeper into the soil profile, out of the growing zone of the plants, and then the calcium that's left over then replaces the magnesium and gives us the structure that we're looking for here on the right. So that's in a very simplistic way in terms of how gypsum does change that soil structure. So in the end, what we have is, if we look here at an illustration from the National Soil Erosion Lab on a water study, where we have a dispersible soil where we don't have adequate calcium, the soil is able to be broken apart. It flows with the water off of the field. As a result, then nutrients move with it. It ultimately ends up in our watersheds, impairing those watersheds, and becomes not only a loss of resources to our farm, but also an impairment to the watersheds. So as we change that soil structure, flocculate that with gypsum, it becomes structurally very stable. Then the water can flow through that soil without moving it off. Look at some research in terms of what's happening here, in terms of nutrient losses through soil loss. Here at the University of Wisconsin had 2 locations, and as they increased the rate of gypsum from 0 to 2 tons per acre, you can see that we have a reduction, a significant reduction in the amount of soluble reactive phosphorus moving off of the soil. So that's an important improvement. If we look again at the National Soil Erosion Lab at Purdue and look at the blue bar representing the amount of water running off of the field, by adding gypsum to that soil, flocculating the soil, creating aggregation that allows the water to move down into the soil profile, we've reduced the amount of runoff by as much as 20%. If we look at the tan bar, which is the soil loss that goes off with the water, you can see that we've reduced that almost 60%. And then if we look at the soluble reactive phosphorus, the nutrients that should remain on the field and be used for crops, you can see that it has been reduced almost 75%. So we've reduced not only the amount of water running off the field, but we've reduced the amount of soil moving with it and significantly reduced the amount of nutrient loss as well. So these two photos show the impact of gypsum on drainage in terms of the soil quality at planting time, and then the ultimate impact on the crop later on. It's important to get the water moved down through the soil, and the gypsum has allowed that, which then improves the crop quality then after that. All right, now to further take a look at water management of the soil, it's very important that our soil be able to receive water and let it infiltrate and conduct down through the soil profile during rainfall events. And this is some work that was done by the Soil Erosion Lab at Purdue University, and basically what this chart is showing us is that the gray bars represent the amount of calcium in the soil. An optimum level of calcium is 74%, which is base saturation. And the vertical line is showing us inches of water per hour that can infiltrate into that soil. And as you can see, when the calcium levels are very, very low, 33, 41%, we're only getting 1/10 of an inch of infiltration of water into the soil per hour, which is nearly sealed, and that's not acceptable. If we balance the calcium, bring it up to the optimum level, we've increased the water infiltration by 5 times. So that's having a huge impact on that. Although a 1/2 inch of water per hour infiltration rate is still not acceptable for no-till agriculture. So the green bars then represent the impact that gypsum has in this environment. And as you can see, by using gypsum as a calcium source and flocculating the soil, we have increased the water infiltration rates almost 18 times above what they were initially. So we can expect almost 2 inches per hour steady state infiltration of water into that soil during rainfall events. And from a commercial standpoint, after years of using gypsum, this is exactly what we see. Heavy rainfall events, we do not have the ponding that we had previously. Obviously, we're all dealing with the impact of drought this year, some more than others. But I wanted to touch base on this. We're finding that gypsum absolutely helps combat drought conditions. Increased, faster water infiltration, like I just mentioned. And then because the gypsum moves down through the soil profile and aggregates that soil deep into the profile, we're increasing the water holding capacity of that soil. So more water holding capacity and more depth of soil receiving that water and receiving roots, we have a much higher level of water storage, which, as illustrated by this particular photo, during a drought in 2008, it has a huge impact in terms of the crop vigor during these dry periods versus where the gypsum was not used. Here's the reason why. This is the soil where that field was located. The gypsum has aggregated the upper A horizon, the 12 inches of topsoil where this crop is growing. But then as we move down into the subsoil, we find that it has moved into the subsoil, and earthworms and night crawlers and other biological systems have moved down with it. Water during heavy rainfall events is moving down through the soil profile. And if we move on down deeper into almost 5 feet into the subsoil, into what we call the yellow, previously dead subsoil, we can see that the gypsum has moved into the subsoil. The soil biology has followed it. Earthworms have filled this subsoil with channels. They have brought down black organic material from residue, and now the crop root is in this environment at 5 feet into the subsoil, getting oxygen, nutrients, and moisture during the drought. And that's why we see the crops surviving much better during these dry weather conditions. Gypsum as a nutrient source contains 20% calcium and 16% sulfate sulfur. sulfur sulfate is the form used by the plants. And the reason that this is important is that we are seeing a depletion of sulfur in our soils throughout the Midwest currently, and that's related back to something Patrick mentioned earlier, and that is the Clean Air Act of 1990 has our power plants scrubbing the sulfur out of the flue gases, and so we're not getting the deposition that we used to, and as a result we're seeing sulfur deficiencies in our crops. If we take a look at some research on this sulfur deficiency issue at Ohio State University, we're finding that gypsum applied for sulfur had an increase, in this case, a significant increase in yield of 11 bushels per acre on corn. Ohio State alfalfa research done for a 3-year period, 2000 to 2002, we saw an 18% increase in alfalfa yields as a result of the application of gypsum for sulfur. So with that, I apologize for the technical issues we've had at this point, but now I'd like to turn the session over to Dr. Torbert.
Yes, I'm Allen Torbert. I work for the U.S. Department of Agricultural Research Service, and on the screen you should see a quick poll if y'all take time to answer those real quick, and we'll get started with the rest of the presentation in just a minute. For y'all that don't know, the Agricultural Research Service is the research arm of the U.S. Department of Agriculture, and we have labs scattered all over the United States. And my particular lab is the National Soil Dynamics Lab that's located in Auburn, Alabama. I wanted to talk just a little bit today about some of the research that we're doing in the ARS with gypsum, and looking at the potential of using this as a soil amendment to improve production. So we've been talking about some of the benefits of gypsum to improve water infiltration and control soil erosion, crusting, nutrients for crops, and alleviate the effects of soil acidity. But one of the other ones is reduce contaminants in water runoff, is one that we're particularly interested in here in the Southeast. We started a multi-location gypsum study focused on improving the crop and forest production and reducing phosphorus losses on the erodible soils of the South. The research goals were to establish rates of FTD gypsum in poultry litter, to document improvements in water quality, and to develop guidelines for use of FTD gypsum for us in the South. And the locations where we were conducting these studies were in Georgia at the Watkinsville lab, that was headed up by Harry Schomburg. Here at our lab, at the National Soil Dynamics Lab in Auburn, headed up by Dexter Watts, and at the National Sedimentation Laboratory in Oxford, Mississippi, headed up by Fred Roden. At the Oxford, Mississippi, the soils were the silty loam soils, and they had 2 sites at Verona, Mississippi, and the Milam, Tennessee. And at Watkinsville, there were the Piedmont soils of the Georgia region. Here in Alabama, we conducted the studies mainly at the E.V. Smith Research Center in the center of the state. This is a large research center for Auburn University. We also had some ongoing studies up in the Sand Mountain research area, because that's the area where our highest concentration of poultry production is in the state, and could benefit from the benefits of reduced phosphorus losses. And we have some ongoing studies too in the Tennessee Valley, which is some of our silty loam soils, and that we'll talk a little bit later. The studies at Auburn and at Watkinsville were focused on the poultry litter production and the impacts with FTG gypsum. We were concentrated on poultry litter because that's the animal agriculture that has the highest concentration here in Alabama and in Georgia. And for the study, we looked at increasing levels of poultry litter as a fertilizer source, and as the combination with gypsum as increasing rates up to 4 tons per acre in every combination thereof. And here's just some pictures of the study sites in Watkinsville, which you see where we raising Bermuda grass, and then here's some in the at the Auburn site at the E.V. Smith Experiment Station. We didn't always find a yield response, but we did find that generally we had a positive trend. Here's some the results from one of the years of the Vernograss in the Watkinsville, where we did see a positive increase with increasing levels of gypsum. But we really wanted to focus on the water quality issues, and that's because of the large impact that phosphorus has for impairing waterways in the U.S. And some 45% of river miles are impaired in the U.S. according to the EPA, and 47% of the lakes. And agriculture is considered to be one of the major contributors to these problems, and phosphorus losses from animal agriculture is the main culprit. And down here in the southeast, that focuses on the poultry industry. What we wanted to do is to look at gypsum because of its impact with soluble phosphorus. When you have a soluble calcium available, it will form insoluble calcium phosphate complexes, specifically hydroapatite and fluoroapatite, are compounds that will form, and then they become insoluble, and then it doesn't present a problem for the environment. So we wanted to look at studies looking at how this might happen in the potential using gypsum, and the tool that we used was the rainfall simulator. Here's some pictures of the rainfall simulator. This tool just generates the conditions that you have with a rainfall event sufficient enough to create runoff. And then we isolate an area in the field where we can look at the impact, where we apply our different treatments, and then we can look at the rates of runoff and the rates of therefore the infiltration, and then measure the losses from the field. And so with this, we took because of the difficulty of doing these types of studies, we took a subset of the plots to look at, and basically we just looked at the highest rate of poultry litter with our increasing rates of gypsum, but then we also included the controls of no gypsum, no poultry litter, and 4 tons of gypsum with no poultry litter. And for these runoff plots, then we captured the runoff that came out and did different time intervals. We took the runoff for a 60-minute interval, and we took samples every 10 minutes. And we also took a cumulative sample so we could look at what the impact was over the entire event. We looked at both the unfiltered samples, which was the total nutrient compounds, but we also looked at the filtered, because this is the dissolved component of the runoff, which has the most direct impact on the environmental concerns. Here's just a picture of some of the runoff that we captured in these studies, and you can see the bottle on the left shows where we added 2 tons of gypsum with our poultry litter. The one on the right shows where we had no gypsum added, and you can visually see that the water is cleaner, even if it's coming off a pasture situation where we had very little sediment losses. We still have a cleaner water source coming in when we apply the gypsum. So if we look at some of the results, here's some of the runoff data that we collected from our Watkinsville lab. We did this in several different years. These are examples from 2009 and 2011. And at the bottom of you see the time of the runoff event, and as you see going up the y-axis, you have the percentage of runoff. The top line that you see here is where we applied no gypsum, whereas the bottom lines is where we had the highest rate of gypsum. So you can see that we were decreasing the amount of runoff due to the fact that we were increasing the level of infiltration. So just to give you some examples of what we were measuring with our runoff sample, here's some calcium that we had in our runoff samples. These first 2 plots are where we had our controls, and then we had an increasing rate of gypsum. And as you would expect, something like calcium, we're providing a soluble form of calcium, so we found that as we increased our rate of calcium, of our gypsum, we were increasing the rate of calcium that would happen in runoff. But what was very interesting was what we saw with our phosphorus runoff, which when we had no manure application, we had almost no phosphorus losses. With our 6 tons per acre rate, we had large losses, but our gypsum increasing rate reduced that dramatically during the time of the runoff. So I thought I'd just show some slides of the different conditions, because we did these runoffs in different time frames. And so we did some regression analysis looking at the slides over time of the slides. Okay. So this first one is just to show you the worst, what we call the worst case situation, where we applied the manure or the poultry litter, and we applied our gypsum treatments, and then we initiated the runoff immediately the same day. And so we had the worst condition to have a runoff event with your application of poultry litter. And this shows the increasing rate of soluble phosphorus, whereas x-axis has the increasing rates of FPD gypsum. This particular regression line was created from our 10-minute sampling, and as you can see, with no gypsum application, and we have a very high rate of phosphorus loss, and then we steadily decrease this down as we increase the rate of gypsum. And we're saying similar things at our 30-minute sampling and our 60-minute sampling, with just the whereas the overall rate of phosphorus was reducing, the gypsum was still being effective at reducing it even farther. And so if we looked at the cumulative impact of the whole runoff event, we could see that we had a 58% reduction in the amount of phosphorus that we lost from that runoff event. So we did a similar project where we were looking at it. In this case, though, we waited 6 weeks after we applied the poultry litter, and then during that 6-week period, we had like 5 inches of rain, so we had some very large runoff events. But even though the total level of phosphorus that was being lost in the runoff event, we still saw an effective measure of reduction in the amount of phosphorus that was being lost over the time of our runoff event. And then so the cumulative effect here was a 50% reduction in the amount of phosphorus that we lost. And then we looked at it one last time at the end of the year. So this was our runoff event. It happened 6 months after we had applied our gypsum treatments in our poultry litter applications. And we saw, again, while the total amount of phosphorus was much reduced from what we saw from our immediate runoff, we still were seeing a reduction with our gypsum application even 6 months later. And so the cumulative effect from that, we saw a 34% reduction in the amount of phosphorus that we lost. We also did some studies looking at a different method of applying a different method during the rainfall simulation. In this case, we were worried about the runoff from the not from the impact of the rain, but after the runoff event occurs, you have the accumulation of the water that's moving off the field, and we wanted to see if the gypsum could be effective at intercepting some of the phosphorus as it moved off the field. In many cases, in the situation where you're using poultry litter, they'll have a filter strips or buffer strips that they have at the edge of the field that intercepts some of the contaminants that are moving off the field. And what we did was we wanted to examine if the gypsum could be an effective tool to improve the effectiveness of these buffer strips. And so this is a slide showing what we found in that case. And the first bar here shows the impact of just the buffer strip by itself. And so the buffer strip was removing somewhere around 15 to 18% of the phosphorus that was moving off the field. But when we added gypsum, we dramatically increased the effectiveness of this buffer strip, and then up to about 40% reduction when we used the higher rates of gypsum. So just so we can be thorough, we wanted to look at what else was coming off, especially in the context that the EPA is concerned about the FTG gypsum being causing other contaminants. So we looked at what else was in the water. For a big one of concern was the mercury, and this slide just demonstrates that we found no level of mercury in these runoff samples down to 50 parts per billion. And then this is just a list of some of the other elements that the EPA was interested in that we also did not find at the 50 parts per billion level. And just a list of some more that the EPA was interested in the dissolved arena that, again, we did not find any indication of these in our runoff samples. And so this was one of our first runoff events, and we had these samples done at an EPA sanctioned lab, but they since decided they wanted to even have it detection limits below the 50 parts per billion level. So we've sent more samples off, and this time it went to Rufus Cheney's lab, who's heading up some of the risk assessment, and he's doing his samples at an even lower detection limit. But so far, he's found nothing to be concerned about. And now I want to shift gears and talk a little bit about what the researchers was finding over at the National Sedimentation Lab in Oxford, Mississippi. And at this lab, they were more concentrated on row crop production, specifically cotton and soybeans, and also included the conventional tillage versus no-tillage treatment. This work was headed up by Fred Roden. And I want to just give a little bit of his results that I've gleaned from some presentations. The first one is just to show some of the soil tests that were measured with depth for the nutrients, and you can see as you increase the depth, the level of calcium and sulfur both increased. These lines represent the higher levels of gypsum. Now that's not to be surprising with sulfur, because sulfur tends to move readily through the soil profile. But this clearly demonstrates that the calcium is also moving through the profile with the gypsum applications, and with a no-till application, this demonstrates that is a method for you to move calcium through the soil profile that you may not be able to do with a lime application. So Fred also did some soil physical characterization. This is just a slide of some of the soil cone penetrometer equipment. The cone penetrometer just inserts a rod through the soil, and it measures the force needed to press through the soil. This particular one measures several at the same time, so that you can take multiple measurements in different positions in the field. And this is just a measure of how hard the soil is, in a sense, and how hard it is for a root to move through insert through the profile. And these are some results that he found at the Milan, Tennessee area. He took these measurements down to 12 inches, and he took them at 3 different row spacings. One was in the middle of the row, one was at the wheel tract area, and one was in the non-wheel tract area. And what you can see is as they increase in both the conventional till and the no-till, as you increase the level of gypsum, you had a tendency to reduce the cone penetrometer measurements, and so it indicates that you would have increased rooting capacity in those soils. They also wanted to follow the soil moisture. The important part of it, having increased infiltration, is you hope that you would have increased moisture in the soil for the crop production. This is some measurements that were taken with TDR, which is a electric conductivity method of measuring soil water, and they took this throughout the growing season in both the conventional tillage and the no-till plot. And what he found was that the no-till, the conventional till plot showed little difference until the end of the growing season, when about 3 tons per acre held more water, while the no-till showed a more consistent advantage at the 3 tons per acre treatment, and with the differences starting early in the growing season. And the result is we had slightly higher soybean yields in the no-till that may have resulted from this increased moisture. At the Milan, Tennessee, they also used TDR in 2011 year, and from the top 45 centimeters. And I know this is a lot of data to look at, so just to sum it up, with the exception of 2 days, the 3 tons per acre had in the no-till plots consistently had higher soil moisture, and in that year the no-till cotton yields were higher. So the tentative results from Fred's work is that he did have the increased infiltration rates and reduced runoff losses. The concentration of the fine sediment size in the runoff was reduced, and he increased the soil moisture storage capacity. He found some evidence that he was remediating some of the soil acidity associated with extractable aluminum, and that he was supplying economic source of plant-available sulfur and calcium. And then the bottom line was that it was increasing yields in the no-till cotton at gypsum rates up to 2 tons per year. So I wanted just to finish up and talk about some of our newer studies that were going on in conjunction with some of the efforts from GYPSOIL. We started a series of studies up in the Tennessee Valley, and as I mentioned, these are more of the silt-loam soils that we have here in Alabama, and we believe they may be some of the more responsive to our gypsum application. We're planning on concentrating more on the soil physical measurements with this study, looking at things like double ring infiltrometers, and we're looking at the Cornell infiltrometer, which uses simulated raindrops to help measure the infiltration rates. We're also going to do electric conductivity, and we're going to look at penetrometer readings, and then with different methods to measure not only the infiltration but the porosity of the soil, which is a measure of how the structure is being formed. That was just where I would just conclude that we do have seen that gypsum can improve the soil physical properties and improve aggregation. That has led to increased infiltration and reduced runoff and improved water holding capacity, and a very important one to us, it reduces the erosion losses and the nutrient losses, especially phosphorus. So I'd like to thank anybody and that took time to participate, and I'll turn it back over to our host.